Thank you for the introduction, so I can skip that. Thank you so much for inviting me here. It definitely gives me a unique opportunity to really expand beyond the conventional laser plasma community and introduce some of our recent results to the astrophysics community. Hopefully this will generate some interest. Today specifically, I want to focus on pair production via photon-photon collisions in laser-irradiated plasmas. Sorry, it's asking me a lot of questions. I'm going to just skip that. This work has been done over the last couple of years, so a lot of people have contributed. So I want to start by acknowledging their contribution and thanking them for the fruitful collaboration. I particularly want to stress that most of the results that I will be showing you today were obtained by my former student, Yutong He, who is currently working with Chris Richards at York. As we've already heard today multiple times, pair creation in astrophysics is a very important process because it is responsible for creating electron-positron plasmas in a lot of different settings. Of course, we're interested in trying to do this in the lab, but achieving an appreciable yield in laboratory experiments remains a serious challenge. There is a good reason for that. There are actually two reasons for that: the smallness of the cross-section and the high photon energy threshold. Fortunately for us, the laser technology is developing at a very rapid pace, and currently we have access to multiple multi-petawatt laser facilities. And what I would like to communicate to you today, that these facilities can potentially offer us a solution. This has been already extensively examined during the recent multi-petawatt physics prioritization workshop, and we did write a report, so if you're interested, please definitely take a look. It might be an interesting document. What really came out of this process is a crystallized vision that for the laser plasma community, one of exciting long-term goals would be to create a microscopic relativistic electron-positron plasma. Thomas already set the stage for this talk, talking extensively about this earlier. Of course, this is a very ambitious and a very difficult goal to achieve, and because of that, we need to get there through multiple stages, and one of them would be a near-term goal of, at the very least, demonstrating appreciable positron yield from light in a single shot, experimentally, not in simulations. You're laughing, but yeah, it's a problem. As we've already heard today, the dominant pair creation channel in astrophysics is, of course, an interaction of a very energetic photon with a very strong magnetic field. Unfortunately, because this does require an extremely strong magnetic field and we cannot create those currently in the lab, so we are not able to directly recreate this channel, but there are two other candidates that are more suitable for experiments and that are potentially equally exciting. These are the multi-photon process that involves the laser field and the two-photon process. So let's take a closer look. The reason why I am differentiating these two, even though both of them involve gamma rays, is because they require very different approaches for their implementation. So let's first take a look at the multi-photon or the nonlinear Bright-Wheeler process. In this case, what we really have is an energetic gamma ray that is going through a laser pulse and decays into a pair. This requires multiple optical photons. This process is sensitive to the laser intensity, and on one hand, this is good news because as we continue to increase the laser intensities due to the progress in laser technology, we can potentially make this process efficient. The bad news is that the current intensities, and I will show you them on the next slide, are not really anywhere we want to be to make this process really detectable in a single shot. Now, there is another potential candidate, and this is the two-photon or the linear Bright-Wheeler process. In this case, you just have two energetic photons. If their energy is sufficient, they can collide, annihilate, and produce an electron-positron pair. In this case, as you can see, the laser field is not directly involved at all, and this really releases us from this requirement on the laser intensity. Of course, nothing comes for free, so we, as a result, substitute one requirement by a requirement to have a dense population of multi-MeV gamma rays. And my main message today, I will show you over the next, whatever, how many minutes I have left, that we can potentially, with currently available laser intensities, satisfy this requirement and produce a lot of electron-positron pairs. So looking forward, in terms of the long-term trajectory, the expectation in the community that over the next, let's say, 5 years, we will continue the improvements and laser intensities will eventually exceed 10 to the 23 watts per square centimeter. And looking along this long-term trajectory, the focus should be on the nonlinear Breit-Wheeler process because of its increased efficiency with high intensity. However, if we're talking about making immediate and near-term progress, we need to evaluate what we actually have available in the lab. So currently, there are multiple laser facilities that can shoot at the multi-petawatt level, and in some cases, the power can even reach 10 petawatt. This translates into having laser peak intensity slightly below 10 to the 22 watts per square centimeter. So under these constraints, it is the linear Breit-Wheeler process that is really the preferred candidate for detecting a lot of positrons in a single shot. And this is why our focus is and has been on near-term experiments designed to observe the linear Breit-Wheeler process. So the objective of my talk today, because I'm talking to a very diverse audience, is really just to review some of our recent simulation results on pair production by the linear Breit-Wheeler process. And here I'm emphasizing that this is inside laser-irradiated plasma, so there will be some plasma physics involved. The rest of my talk is basically consists of 3 parts. I will first spend a little bit of time explaining how exactly we simulate the linear Breit-Wheeler process in our PIC simulations. And then I will show you what kind of predictions we were able to obtain for a setup where you have just a single laser pulse, and then I will conclude by showing a more optimistic scenario where you are able to utilize 2 ultra-high intensity laser pulses. When we first started this journey and we looked at the available computational tools, it became immediately very clear that we were not well equipped to simulate the linear Breit-Wheeler process in PIC simulations. So we started thinking of how to do this and what kind of improvements need to be made. When we're talking about simulating the linear Breit-Wheeler process in laser plasma interactions, we're really talking about kinetic simulations because these interactions are inherently kinetic. Typically, in our community, we use particle in cell codes, so this seems to be the best way forward. So in such a simulation, the fields are simulated on a grid, and the plasma is represented by actual particles, but they are marker particles. Each of them represents a lot of individual electrons or ions. Now, in order to make this simulation at least trustworthy to some level, we need to resolve the laser fields. So this means that having at the very least 20, in some very optimistic situations, maybe you can put 100 cells per wavelength, with the typical laser wavelengths being around 1 micron. Now, you're probably wondering why I'm bringing this up. I'm bringing this up because when we're talking about the linear Breit-Wheeler process, we need to simulate electromagnetic radiation that is representing 1 MeV photons, whereas the laser itself represents optical photons with energy of roughly 1 eV. This is a huge discrepancy, basically a factor of 1 million in terms of the wavelengths. So the bottom line here is that if we just want to run our simulation and try to reproduce this kind of radiation, it will be absolutely impossible because we just don't have enough resolution. So at first, this seems like a total disaster, but actually because the discrepancy is so huge, this gives us a significant advantage and a welcome simplification. The photon wavelength is so small that it's actually smaller than the typical distance between the electrons in our plasma. As a result, we can just treat the emission as incoherent. So this is first simplification. The second simplification comes from the fact that we're really primarily interested in emission by ultra-relativistic electrons when they get deflected. And these electrons, of course, emit primarily in the forward direction. So we can neglect this opening cone and essentially treat the emission as being directly forward. And this is exactly what has been utilized to develop a module, an emission module that probabilistically creates forward-moving photons. So they're emitted as individual particles in the simulation. While at the same time, the effect of the radiation reaction is included by introducing the electron recoil with the electrons experiencing that after each emission. This process, as we've already heard today multiple times, is controlled by a dimensionless parameter. I will refer to it as chi-e here. We will shortly discuss the structure here because it is important. But for now, all I want to emphasize is that this parameter determines both the power and the typical energy of the emitted photons. Now, once you use the code that has this module, you actually have photons as individual particles that are moving all over your simulation box, and then you can transition to simulating the linear Bright-Wheeler process simply by looking at it as binary collisions of those microparticles. The way we do this is that we randomly pair them. So we take a single cell, we randomly pair the photons, calculate the probability, and based on that probability, each time step, we decide whether to emit or not pairs, and their momentum is determined based on the differential cross-section. So far, it's pretty straightforward. The part where you have to be careful, because in this case, you do need to annihilate the photons when you produce the pairs. So you want to make sure that your random pairings meet these two important criteria. On one hand, you want for the pairings to be, for that number to be big enough to exceed the number of possible pairs that you actually produce, because otherwise you will be severely undercounting. On the other hand, you want it for it to be small enough, otherwise you select photons twice and you overcount. We have implemented both of those criteria, and the module is working. I will show you the results shortly. It is also ready for the public release, so it will become available with the official Epoch release later this fall. So of course, this is like an open access, open source code, so anybody of you who's interested are welcome to download and use it. It was one of our goals to actually do this for the community. So now with this, like equipped with this tool, we can start asking questions about the physics. So the first question would be, if you just have a single ultra high intensity laser, what exactly can you do in this case? The answer is surprisingly simple, and you're probably wondering, like, why is it so simple? The reason is exactly the same, because there was no module to actually evaluate what happens. And so once you put that tool in place, the answers start coming out. In the beginning, they are quite simple. So I will start with the answer, and then I will explain why things work the way they do. So in this setup, we take a dense plasma and we irradiate it by an ultra high intensity laser. Here, I deliberately keep the intensity well in the range of what is currently available, like at the upper end, but still reasonable. The plasma, as you can see, is dense, so the electron density is twice the density of the classical cutoff density, but because the laser is so intense, it makes electrons ultra-relativistic, and as a result, they become effectively heavier, which renders this plasma transparent, so the laser is able to go through. As it goes through, it induces a lot of emission. It is shown here. Basically, what you're looking at is the photon spectrum. On the vertical axis, on the log scale, you have the photon energy. This is the angle. The left panel is for the forward emission. The right panel is for the backward emission. For reference here, the 0 corresponds to 1 MeV photon, so you see that we do emit quite a lot of them in the forward direction, and not surprisingly, it looks more like a beam. What is more surprising and unexpected is that you have a lot of emission in the backward direction as well. Of course, it is completely uncollimated. It goes like all over the place, so at first you might think that this is completely useless, but it turns out that it's not a problem at all. By taking a look at the density of the forward and backward emitted gamma rays, and this is just a single snapshot, we can see that the two populations overlap, and this overlap is sustained as the laser propagates forward. So the takeaway point from this is that the plasma is able to self-organize to create a moving photon-photon collider. And using our module, we calculated that for this simple setup, we can expect around 10 million pairs in a single shot. For comparison, in that pioneering SLAC experiment, the yield was roughly 1 pair per 100 shots. So this would be a significant improvement, and this is why we're trying to go in this direction. Now let's take a look at the physics of why things work this way. And let's first look at the forward emission. The forward emission is directly linked to direct laser acceleration of electrons. As commonly the case, we characterize the strength of the laser field using this dimensionless parameter A0. If it's much greater than 1, it tells us that the laser would produce ultra-relativistic electrons. So in our case, the value of A0 is 150. So not surprisingly, when an incoming plane wave of this amplitude irradiates a single electron, and as this electron starts to gain energy, it very quickly becomes ultra-relativistic and experiences a very strong forward push from the laser magnetic field. So as a result, instead of sitting in one place and oscillating up and down, the electron is propelled forward. So this is a representative trajectory. The main point that I want to make here is that most of the energy in this case is in the forward direction. So the laser pushes the electron forward. When we're talking about the plasma, the laser is able to push this way a lot of electrons. So it shouldn't be very surprising that as the laser propagates, the laser field is not shown here. It is able to create a very strong longitudinal electron current in the plasma. The key here is that our plasma is very dense, so this current can be so strong that it can generate and sustain a quasi-static azimuthal field. This field is shown here, so it is shown in blue and orange. The field can be so strong that it is in the multi-gigagauss range even for currently available laser intensities. The polarity of the magnetic field matters here, so if you just cut like this across and look in the cross section, you see that the magnetic field changes sign, which means that if you just inject an energetic electron here, instead of performing a conventional gyration here, the electron gets deflected forward, and each deflection by this very strong magnetic field induces emission of very energetic photons. So as you've seen earlier from the spectrum already, this is exactly what enables the emission of multi-MeV photons. What is less trivial here is that the magnetic field is not only responsible for inducing the emission, but it facilitates the energy transfer from the laser to those electrons, so it creates the energetic electrons in the first place. This can be termed as the magnetic field-assisted direct laser acceleration. To understand what is at play here, let's go back to this schematic picture. So each time the electron is deflected, its transverse velocity flips its sign. Now at the electron location, the laser electric field is also oscillating. Typically, this is a problem because those oscillations prevent electrons from continuously gaining energy. But if the magnetic field is sufficiently strong here, the flips of the transverse velocity can be timed appropriately, so the velocity flips as the laser electric field changes sign, and as a result, the two vectors can become anti-parallel and stay this way for multiple, sometimes even 10 laser oscillations. So this allows for the electron to continuously keep gaining energy, and during this entire process, the electron continues to emit forward-directed gamma rays. So far, this is probably quite transparent, but you might be wondering, what about the backward gamma rays? Where are they coming from? To answer that question, we need to go back and revisit the emission mechanism. So if you recall, I said that we are primarily interested in ultra-relativistic electrons that emit in the direction of their momentum. So this means that forward gamma rays are necessarily produced by forward electrons, and backward gamma rays would be produced by backward electrons. This is an important observation because if we now look at chi-e, we see that instead of just being dependent purely on the strength of the field that performs the deflection, it depends on its relative orientation with respect to the electron velocity. Now, for the electron that is flying forward with the laser, the effect of the laser electric and magnetic fields almost entirely cancel out. So we're left here just with the magnetic field of the plasma. And this is why, as I said earlier, electrons that move forward emit primarily due to the plasma magnetic field. So this would be the estimate for their chi-e. Now, for the electrons that are moving backwards, there is no cancellation. And then as a result, it is the laser magnetic field that is primarily responsible for the emission. And as a result, chi-e now is determined by the laser rather than plasma magnetic field. This field is a lot stronger, and this is why, in this case, the requirement on the gamma is reduced, so we do not need equally energetic electrons flying forward, even for the emission of multi-MeV gamma rays. But still, what would be the source of this backward moving energetic electrons? This is where the plasma physics comes in, again, to the rescue. To understand what is going on, let's take a closer look at the laser propagation. So here, the laser fields are plotted on top of the electron density that is shown here in the background in grayscale. The plasma is dense, so the front of the laser pulse is very steep, and as it propagates forward, it piles the electrons up. You can clearly see it here. The ions are not able to respond on the same time scale, so the ions are left behind. Because the ions are left behind, the laser is able to create a longitudinal electric field that is directed forward, and this electric field is moving with the laser pulse. The electrons at the very front that are exposed to this laser field, to this electric field of the plasma, they gradually slow down, come to a complete stop. And then because this field can be so strong, since we're dealing with a very dense plasma, they can be accelerated in the backward direction to energies that can be, for this specific setup, in the range of 100 MeV. And then when these electrons collide with the laser, this is when the emission of the backward directed gamma rays takes place. As electrons are released from this pileup, the laser continues to propagate, and so it basically, like a snowplow effect, it continues to build up the same pileup here, and as a result, the laser is able to continuously maintain this longitudinal electric field for as long as it propagates forward, and this is what sustains this moving photon-photon collider in the plasma. So to recap what we've talked about so far, hopefully I was able to convince you that the two-photon pair production inside a laser-irradiated plasma is not a completely doomed enterprise, but instead it can be efficient already at currently available laser intensities. And the key to making it work is to get into the regime where the plasma can self-organize to create a photon-photon collider. So it's probably for the first time in my career where the plasma does actually what you want it to do and comes to your rescue instead of making life very complicated. Now, sometimes you might be fortunate and you might be able to get beam time at a facility that has, instead of like one laser beam, has two, those multi-petawatt laser beams. So because of that, it is worth asking whether or not this would be a significant advantage, because of course, setting up an experiment with two laser pulses will be significantly more complicated. So one potential setup is shown here. If you do have two laser pulses, you can irradiate the plasma from both ends to create a colliding or counter-propagating setup as the one shown here. Now, before the lasers collide, everything works exactly the same way as we've discussed so far, with each laser pulse creating its own beam of very energetic electrons that are flying forward. Now, once these electrons reach the net plane here, they meet another laser pulse and collide head-on. So this is very similar to what happens with the backward emission in the previous setup, but here the electrons are much more energetic. This dramatically increases chi-e. As a result, the emitted power goes up. This, of course, increases the density of the photons that we create in this region. Now we have electrons moving to the left and electrons moving to the right, so we will have colliding populations of gamma rays, and as a result, we have yet another, but in a slightly different configuration, photon collider right inside the plasma here. Here you can see the yield on a log scale as a function of A naught. We're shooting lasers with the same A naught, so this is A naught for one of the lasers. For reference, for more experimentally inclined people, I show here at the top the laser intensity. The yield is shown here with green markers. So you can see that it is increasing, and for what we can typically expect to get in the experiment, we are approaching around like 1 billion pairs. So this would be almost a 2-order increase by using 2 lasers instead of 1. And of course, if you continue to increase the intensity, the nonlinear Bright-Wheeler process can kick in as well. This very sharp slope here reinforces my earlier message that this process is very sensitive to the laser intensity, and eventually it can even become competitive with the linear Bright-Wheeler process. But for what we can currently try to achieve, really the focus should be on the linear Bright-Wheeler process. So far I have talked about the yield. If you're really cynical, you can say like, hey, like, why did you waste all your time? You can really like look at all the photons and estimate the yield. You don't need to like invent the module and all this stuff. And you would be absolutely correct. What the module that we implemented allows us to do, it allows us to examine the positron dynamics after they're created inside the plasma, which otherwise you would not be able to do. And this provided us with a lot of useful insights. Just as a highlight, I would like to show you one of the questions that we were able to answer. So we were specifically interested whether or not positrons can be accelerated after being created, because this can aid potentially the measurements and the detection of those positrons. Let's first look at some qualitative arguments, and then I will show you the simulation. So if we're talking about a single laser pulse, let's recall that it creates a magnetic field with a set polarity, and the polarity is such that the electrons are deflected in the forward direction. And this is why they can undergo this direct laser acceleration assisted by the magnetic field. Of course, the positrons are positively charged, so they are being deflected backwards, and this is why for a single laser pulse, it's not particularly helpful to have this magnetic field. Now, when we shoot 2 laser pulses, they collide and go through each other. What happens, and that was surprising at first, is that the plasma magnetic field retains its polarity after the 2 lasers pass through each other. And the polarity with respect to each beam is now reversed. So as a result, the situation changes, and it is now positrons rather than electrons who can benefit from the presence of this magnetic field. So they can be now confined in the transverse direction while undergo this magnetic field assisted DLA. It is better to conclude with an animation to make sure that you really believe me that what I'm saying is true. So here in green and purple, you see the magnetic field. So exactly as advertised, the polarity of the magnetic field remains exactly the same after the collision. The circles here show very energetic positrons that we produce. You can see that they are collimated and essentially ejected as 2 positron beams that are going to the left and to the right. I didn't want to burden everybody with the details, but potentially this acceleration can aid the detection of the positrons because it will collimate them, and so you will get more count on the detector. And this takes me to my last slide. Hopefully I was able to convince you today that the 2-photon pair production inside a laser-irradiated plasma can be efficient at already current laser intensities, so there is a way forward. The good news also is that the positrons can be produced with a single laser pulse or with 2 counterpropagating lasers, so there is some flexibility when we're designing the experiment depending on what is available. The key to making this work is the self-organization of the plasma. In both cases, the plasma creates a photon-photon collider with a very high density of the photons, and this is what enables that generation of basically like billions of electron-positron pairs just in a single shot. The only hard requirement in this case is that you do need to work with a dense plasma, a gas jet is not going to work because you're not going to create the fields in the plasma that is sufficiently strong to enable the regimes that I've discussed. So at this point, I would like to stop. Thank you for listening, and I'm happy to take any questions you might have.
All right. Thank you very much, Alexey. I'll go to the back here for the first question.
So you said billion pairs. If you compare pair density with ion density, it's much smaller,
yes.
Right? Well, what's the number? And how far you would need to go in intensity to have enough pairs to begin to strain out this electric field that you have from
in order for the positrons to change the local field configuration?
Yeah, basically when the density becomes comparable to the ion density.
I think in this regime we're like extremely far off, like many orders of magnitude. So I mean, this is like a good question because some people do consider that. So Tomas's earlier talk was focused on that, on trying really to create more like a plasma situation where the positrons can affect things locally. In our case, they really more act like test particles, barely affecting things. Like the density is very low.
How you said billion? I think the
Oh, I mean, I didn't even like calculate the density because we have only like 10 to the 9 positrons, and the density is like the plasma is like overcritical. So you get like more than 10 to the 21 ions.
10 to the 21, the volume is like micron cube times whatever, 100. So I think it's like 1,000, maybe this kind of a number.
Yeah.
Maybe, yeah. Okay, and then another question is about the motion of particles. So you have strong magnetic field and you have electric fields. And so, and the field is quite strong and the particles become kind of magnetized. Should one think about the motion as a cross-beam drift, or it's like wrong thinking?
So, yeah, thank you for that. When I was preparing the talk, I was choosing like how far to go into details because I didn't know the audience that well. So surprisingly, I have worked on direct laser acceleration in different regimes. So usually when A naught is 10, it is the transverse electric field in the plasma that really dominates. Surprisingly, at this high values of A naught, the electric field is relatively weak if you normalize it compared to the magnetic field. So this is why I was primarily focused on the magnetic field. So the charge separation electric field, the plasma is able to basically kind of like shorten that out. And so this is why the magnetic field is much more dominant. So maybe it's, I'm not really prepared to say like 2 orders of magnitude higher, but like when you compare, even though the transverse electric field can be incorporated, to simplify things, I just basically like threw it away from this analysis. But you can definitely look at it as a drift, and I'm not sure like how much it will change because you see the magnetic field is like it changes its sign across the axis. So the magnetic field itself already induces the drift. One thing that I did not show, for example, for a single laser pulse, you produce a lot of positrons. Only 10% of them get picked up and accelerated forward. 90% of them actually drift backward, the same way that I was showing here. So the laser is gone, we produce those positrons and they drift backwards. So just the magnetic field itself can already induce the drift because it's a little bit different from a configuration where you have like a uniform magnetic field and an electric field and you get an E cross B drift.
Yeah.
So from what I'm typically seeing is that this non-uniformity of the magnetic field and the change in sign induces the drift of the positrons in the backward direction.
Thank you.
All right, I think that there's a question over here first, and then we'll go to Chris after. Do you want to use the mic here?
Thanks for the talk. One question I had was about the parameter regime. In particular, do you have a sense of what the optical depth, let's say, for these gamma ray photons? In other words, what fraction of them actually escapes the system? Unfortunately for us, 99.999
escape. So it's even like very difficult, even when we create this like very dense plasma for the collision. So I recall the probability is something like maybe like 10 to the minus 5 for them actually to collide and to produce a pair. So I mean, we're trying like to fight like the unavoidable fact that the cross section is really low and we're dealing with small scales here. But the situation is not completely hopeless, because if you look at the number of pairs and how much energy from the laser we actually convert into those pairs, it's a very, very tiny fraction. So there is a lot of room here for optimization and coming up with maybe a better setup, or just simply optimizing the parameters to build up the yield. But unfortunately, because the size is small, the density of the photons can be quite high. It can be almost 600 times the critical density for those like relevant like 100 keV photons, but still it's not enough to basically for them to be like for all of them to produce the pairs. Most of them just like escape and come out.
So how narrow band does the pump wave have to be for this Betatron-induced DLA to work?
Good question. So it's a good but complicated question, and I need to think for a little bit how to give an answer that is not too complicated. So this is like a very oversimplified picture here. So what I mean, since we have a little bit of time, right? So what happens in reality here is that as the particle is flying forward and it's experiencing those oscillations, so those oscillations depend on the particle's energy. Now, the laser field experienced by the particle does not see it at the same frequency as you see in the lab. So that there is a Doppler shift, because otherwise we would never be able to match the two frequencies. So the only reason why the match happens is because the electron is relativistically flying forward. So it is possible to match the two frequencies. Unfortunately, the energy dependence for the two frequencies is very different. So what happens is that even if at some point you are in resonance, it's not really truly like a resonance. As soon as you start gaining energy, the frequency detuning takes place. So then the question of how can you make it happen, and how like am I like a liar when I said you can have like 10, maybe 15 oscillations where this condition is satisfied? The way you can do this, and it seems completely counterintuitive. So here we're talking about the laser propagating in a dense plasma. In a dense plasma, you have a phase velocity that is not equal to the speed of light. So it's actually higher than the speed of light. This seems like the bad news. But what happens is that if you plot the ratio of the frequencies, like the Betatron frequency to the Doppler shifted laser frequency, in vacuum, you would get a monotonic increase with energy. So you're basically doomed. You go through the resonance and then you detune and the energy gain stops. What the superluminal phase velocity can do, it can change that dependence and it can make it non-monotonic. So if the plasma conditions are just right, you're able to keep that frequency match for quite a long time, because first the ratio like decreases, goes a little bit below what you need for the resonance, and then you keep gaining energy, you start detuning, but you actually come back to the resonance. Then eventually you will overshoot, but that would, it's not exactly probably the answer you were looking for, but.
Someone's got a question over here.
Hi, Alex. Thank you for the talk. Could you come back to the slide where you showed the counter-propagating setup? And particularly the enhancement in the yield. After there was another. Okay, so okay, perfect. So actually, it's already there. So you've been also taking into account like some pairs coming from the nonlinear Bright-Wheeler.
Yes.
So what if you had the two competing? How you will make the difference between the two kind of pairs?
So you're asking how would you distinguish between
exactly? I mean, if because you're enhancing by 2 orders of magnitude, but then on the top of this, you get another process contaminating your.
So we had a separate paper where we looked at that because, of course, this is like very important, and this is actually why we also plotted the beta Heitler here. So like at least it can kind of like eliminate that. The only way to eliminate them is to look at the scaling, because in I should probably go back here. So in this setup, as the lasers propagate, they also get depleted. So it will depend on the length of the channel. This is what I did not touch on here, and the density inside the channel. So it is possible for the lasers to be sufficiently depleted that, because as we said, that the nonlinear Brightwheeler is quite sensitive to the intensity. So here, this is the intensity before
Exactly.
the lasers
So your
even.
A0 will be your juice during the path.
Yeah. So so by doing that, you can identify the regime where you basically completely eliminate it. And so probably you wouldn't do this like in a, even though I say like a single shot, but you need many shots to actually to figure out the trend. But the trend would be probably to change the length and to like rely on the, one of the parameters would be to rely on the depletion.
Okay, thank you.
Okay. Yeah.
Hi, Alex. Thank you very much. So, question related to the previous question about the detuning. So, you say that having superluminal phase velocity helps with keeping the tuning for the resonance longer. But it looks to me that in your parameters, you probably are in radiation reaction dominated regime, or so how does have you looked into how does this couple with the superluminal phase velocity tuning part? So is it, because I know that the radiation reaction helps tuning as well.
So thank you for that. This is like another thing that I didn't have time to discuss. Like in our, like we're preparing this for publication with Luis. So we looked at, it is, to get into this regime where you try to mitigate detuning with the superluminal phase velocity, you need to make like certain arrangements because you need to like figure out what kind of plasma parameters to take and how to get this done. But once you get into that regime, as you correctly indicated, if it is really efficient, even at a naught of 10, what we see is that the gamma can become so high that you can start emitting. So potentially, like if you really can get into that regime, you need to start taking into account the radiation reaction. So the energy gain that you can predict based just like on single particle dynamics and this like mitigation of the detuning, it can be significantly less, but it's almost kind of like the chicken and the egg situation that first, without that detuning regime, for some values of A0, you cannot even get into the regime where the radiation reaction matters. So you need to get into this regime where the superluminal velocity matters. So then the energy can keep going up, and at some point you start emitting where it starts to interfere with the electron dynamics, and so it prevents from energy going up. So we clearly see in simulations that like if you completely turn off the radiation reaction, the energy can continue going and it can be maybe 3-4 times higher.
Okay, I'm going to take the opportunity to ask one last very small question. How well known are the cross sections for the photon-photon collisions? Is there a big error in them? Like how are they known, or where do they come from?
Can I punt this to Tom? He's looking at me, so that.
That's a very good question. So I think this is what we're using vacuum cross sections. And we know that the presence of a background field absolutely modifies cross-sections for 2-to-2 processes in QED. We have the interesting problem that our background field, it has, temporal and spatial structure. But if you look at, say, what we think is, if it happens reasonably quickly, and so it's taking place in a mixed E and B fields, there should be modifications to the kinematics, especially near threshold. Because if the background field can do work, you can cheat your 2mc² threshold by getting the field to do some of that for you. And it looks like those corrections scale something like chi over center of mass energy all squared. So for the kinds of parameters that we have, I would say they weren't game-changingly big. I'm leaving myself enough space to change my mind later. But it was one of those things where there is a limited amount of theory work, actually, on that kind of background, and it will be really interesting to see what happens, because we know there are resonances and kinematics changes. I hope that helps. Absolutely, yes.
All right. I think we've come to the end of our time for the session, so we've got another half an hour for coffee. So let's thank Alex and Christopher again.